At page 74, we're talking about the integral test statement here. I'll just read it and then I'll talk a little bit more about it. If f is positive, continuous, and decreasing, so the decreasing part's important, for x greater than or equal to 1, and a sub n is equal to f of x, that's kind of an iffy concept there. I'll get to that in a sec, though. Then the sum from n equals 1 to infinity, I apologize for the notation there, it's the only way I can get it to fit in one line, and the integral from 1 to infinity of f of x dx, so that's the improper integral, either both converge or both diverge, right? So this part always kind of stuck in my craw a little bit, only because they're not related concepts. I mean, in the sense that one is discrete and the other is continuous. All right, so a sub n gives you a set of points that are very often not something that could be represented using a function very easily. All right, and in some cases, I mean, you could end up with a situation where it's not a function at all. All right, so we have to make that assumption that it's more like a sub n could be traced out using a function of x. All right, so what that's saying is, and I mentioned this before, the idea of connecting the dots. So can I pass a function through these points? I missed a couple of them, but that's not intentional. This is more like I can't draw / hand-eye coordination. Can I pass a function through these points much like you would with a regression model? All right, so this would be my f of x. All right, so if that's the case, then you might be able to apply the integral test. All right, and that's because, again, it says if f is positive, so above the x-axis, continuous and decreasing for x greater than or equal to 1. So it could be happening any way it wants to, the function, for values less than 1. But as long as it's decreasing, positive, and continuous after or equal to x equals 1, and it also traces out the path created by a sub n, then the summation and the integral will either both converge or both diverge. All right? So it kind of feels like, well, what does that tell me? Well, if these conditions are met, and I determine, let's say, for example, I determine that this integral converges, then necessarily the summation or the series must converge. Or if the integral turns out to not converge, then the series would also not converge. All right, so a quick example of what that might look like. Let's say you have some points that follow a geometric path. So I'll make them nice large points here. And I'm able to come up with a function that's, I got some funny business going on down here, but then up here it follows the requirements of being appropriate for the integral test. All right, so f is positive, continuous and decreasing for x greater than or equal to 1. So let's say that this is 1. And it can trace out, or it does trace out the sequence generated by the series, then we're looking at something that could be considered an integral test appropriate type of problem. All right, so these are my sketches. Hopefully they're somewhat helpful, but let's dive into an example. All right, let's take a look at number 1. Without drawing the graph, we can still determine if it's something that would be decreasing just by listing out the first few terms of the sequence. All right, so just focusing on a sub n here. That's my a sub n. we'd have 1 over 1 squared plus 1, so 1/2. 1 over 2 squared, 4 plus 1, 5. 1 over 3 squared plus 1, sorry. 3 squared is 9, plus 1 is 10. Once you get a sense of the general trend here, it gets a lot easier. Oh, sorry, it's not 1 on top. I saw the end there, and I couldn't stop seeing ones. All right, so yeah, 2 and 3. Apologies. All right, so 0.5. 2/5 is 0.4, 0.3. So it's definitely decreasing. All right. Now it's a question of, will the corresponding function also decrease? Can we come up with a function that'll trace through those points? All right. So we'll see. But if we can, then we're in good shape. All right. So let's make the assumption. Let's let f of x be equal to x over x squared plus 1. Let's take a look at the picture. I'm going to go back to function mode. If this unit is really anything, it's the unit where you learn, if you're really into the TI calculator, the different modes of the calculator. All right, so x over x squared plus 1. All right, so that's the assumption. We're going to let f of x be equal to that. Now, if it meets the conditions, then we're going to apply the integral test. All right, so the moment of truth. Because otherwise, it's like, all right, well, what is it then? All right, so let's do a zoom 6. Okay, maybe. Let's bring it in. -1 to 1 for the y-axis, because, I mean, in terms of x, we're fine, but in terms of y, it's definitely too... I just lost the word for the opposite of compressed. Expansive, I guess. All right, but yeah, so at 1... All right. Yep, that's positive. It's the highest point. So after 1, it's decreasing. And it looks like it's continuous. Let's see, in terms of asymptotes or imaginary numbers, well, there wouldn't be an asymptote because you can't set the bottom equal to 0 and get a real number solution for x. So we're good. All right, so we meet the conditions. So now we can start the fun part, which is finding the integral over the interval of 1 to infinity of x over x squared plus 1 dx. You might remember that when you have an improper integral, that we define the upper bound, or whatever bound involves infinity, as some variable a. So let a be, or dummy variable, infinity. So limit as a approaches infinity, going from 1 to a. And you might have noticed this even when we talked about improper integration for the first time. I always would say let a be infinity instead of let a equal infinity, because a is never going to equal infinity. Right? It's a placeholder for infinity, and I just didn't want to write let a be a placeholder for infinity. So maybe that little explanation is a little overdue, but I just wanted to make that statement. Just came into my mind at that moment. So we have the x over x squared plus 1 dx. Now I'll make the dx red. I feel like probably never should have went to the black marker there, but whatever. So now I need to integrate this, and the theory, whenever you're beyond the unit of study where you cover a concept, there's always the perspective and perception, teacher perspective and perception, and then also the student. So after a student takes a test, for example, on a topic called techniques of integration, and then maybe that student gets a 100, the teacher's perspective and perception is, okay, well, now you've mastered 100% of that concept, So I can expect you, when you see an integral that looks just like this, to be able to do it in your head with no problem whatsoever. And then, the natural consequence of that is, well, what about the student who got a 70? What about the student who failed the test but is still going to pass the course? I mean, I'm sure they would also like to understand this concept. What I'm getting at here is these techniques of integration, or those techniques of integration that we covered in the second unit, they're not going away. All right. So if you didn't know them then, you gotta start to know them. All right. So you got to take the time, because they will influence your level of success moving forward, and not just in this class, obviously. All right. So I look at this and I say, natural log. And you say, well, how do you know that? And when we talk about natural logs, I'm always looking to see, and especially when I see a rational expression, I'm asking myself, is the derivative of the bottom equal in some way to the top? Well, the derivative of the bottom here would be 2x. Well, that's just a constant multiple away from being x. I'm only off by a multiple of 2. So I can correct for that. So if I were to say, and I'll just kind of continue the work up here, the natural log of x squared plus 1, its derivative would be 2x over x squared plus 1. Well, that's double what I want. So let me slap a 1/2 on that and call it a day. All right. Not really, because I still have to evaluate it from 1 to a. And then I still have to find the limit as a approaches infinity. All right. So I'm going to pop in an a for x. And we'll be looking at 1/2 ln. And we can drop the absolutes now, because anything I put in for x is going to necessarily be positive. Square something and add something to that squared value, it's going to guarantee to be positive. So we're looking at a squared plus 1 minus 1/2 1 squared plus 1. And this is what we're going to apply the limit to. And so where this goes, the summation is going to follow, where the series is going to follow. All right, so I'm going to clean it up a little bit. I lost my ln. My penmanship was actually looking pretty sharp here too. There we are. Okay, so cleaning it up. There's not much cleaning to do. I mean, this can be cleaned a little bit. So I'm going to just do a copy paste job. And now I just need to evaluate this limit. So then I'd be asking myself, all right, well where is this going? Because I know where this is going. That's easy enough. That's constant. In fact, I could even rewrite and say limit as a approaches infinity of this minus limit as a approaches infinity of this. So whether this integral is going to converge or diverge is going to be strictly dependent on the natural log part of it. All right, so you could do it a couple of different ways. One way would be actually to, do it out analytically, and there is value to that in some cases. In other cases, it's kind of unnecessary. We will have to learn how to evaluate, even in the case of natural logs. But for now, let's just pop it in the calculator and see where this goes. This one, I think I'm going to use Desmos. So 1/2 ln a squared plus 1. So y equals 1/2 ln, I'll use x squared plus 1. All right, so as we go out to infinity, it does appear as though this is increasing. It doesn't seem to be leveling off. If you're unsure, you can always expand by hitting that little wrench can expand this to whatever you want. It's never going to, I mean, I don't want to say it's never going to get too large. Obviously it will. But what I'm going to do is I'm going to make this 10 for now and expand this out to, let's say, 1,000. So it's going to increase just at a very slow rate. All right. So let me make this 20, and let me make this 100,000. All right. Still increasing just at a very slow rate. So it's never going to level off. It's always going to increase. It just really feels like it's going at such a slow rate that it might as well level off, but it's not going to. All right. Even though it looks like it is, it never is. It's always increasing. You'd say, oh, well, wait, maybe it's going to 13. No, okay, keep going. Maybe it's going to 14. No, it went right past 14. You know, it'll take a while to get to infinity, but it'll get there. All right. So it just doesn't always seem that way. So this is going to infinity. And then at this point, it doesn't matter what this is going to be because it's going to be divergent. All right. But even still, and to address the question that might be on somebody's mind, what if the other one was infinity? Infinity minus infinity is 0. There's no guarantee it's the same infinity. All right. So there's no guarantee it's going to 0. All right. So this is going to be infinity. So that limit is not converging on anything. And so our conclusion here, so we want to be a little bit more specific with our conclusion here, because what I just proved is that the integral diverges. I never drew a conclusion about the series. All right, so I want to make a statement there. So therefore, the sum from n equals 1 to infinity of n over n squared plus 1 diverges by the integral test. Okay, so there's a lot going on there. It's really a lot of the assumptions and conditions that go into allowing us to apply the test, but then also the conclusion that's drawn, allowing us to, state a final answer. It's like, well, one conclusion is stated directly related to the integral. The other is related to that conclusion, but it needs to be expressly stated also. All right, so now the next one, that's, if I'm looking at my work to start off A, that's actually what I was writing initially before I caught my mistake. So I'm going to steal this and go back and make these. Oh, that was fine. I'm going to make these ones. So we want to check our conditions, and that would be that f of x being equal to 1 over x squared plus 1 is an appropriate function to model this series. All right, so I'm just going to pop that in there. All right, so after an x value of 1, it does appear to be decreasing, positive, and continuous. So we're in good shape. All right, so I'm going to find the integral over the interval of 1 to infinity of 1 over x squared plus 1 dx. All right, and again, we're going to let a be the infinity. Copy paste is a beautiful thing. And again, folks, I hopefully mentioned this in the beginning of the course. I think I did. I don't want to spend people's money for them, but if you have a tablet, iPad specifically, and you're in the market for annotation apps, I use GoodNotes. That's the app that I'm using here, and an Apple Pencil, and it's it. I don't use paper anymore. Let's just put it that way, all right? Because I haven't needed to. It's a very comfortable way for me to write. So if you're in the market, that's my recommendation. Right? And I get no money for it, unfortunately. So I can integrate this based off of knowledge from the previous unit. So the antiderivative 1 over x squared plus 1 is the arctangent or inverse tangent of x. That's happening over the interval of 1 to a. And we're applying the limit as a approaches infinity. Right? So we're looking at the arctan of a minus the arctan of 1, again applying the limit. All right, so there's a couple of ways to handle this one, but in many cases there's that underlying technique that's always going to come into play. If you see an addition, subtraction, break up your limit or break up your integral, break up your derivative, break up your summation. Very often that's going to come into play. So limit of the arctan of a minus the limit of the arctan of 1. Now, arctan of 1, that limit is constant. So that's going to be the arctan of 1. We'll get to what that is in a minute. But the arctan of a, you can figure that out any way you want. If you happen to know, and honestly, you should, the arctangent is, the result of arctangent is an angle, or arc anything is an angle. The argument contained within the inverse trig function, so arctan of a, in this case, that a represents a ratio. Okay? So if you go out to infinity, like what angle are you going to level off on? All right? So you can look at the picture, but ideally you'd be able to kind of just reason that out too. Because if you know the domain for the arctan function, or you know the domain for a tangent function even. So here's tangent of theta, or no, I'll say tangent of x, y equals tangent of x. You're looking at something like, and we talked about this way back in the first unit. Here's negative pi over 2. Here's pi over 2. You're looking at a graph along these lines. I'm not an artist, so it's the best I can do. All right. X becomes y becomes x when you find an inverse. Right? So the lowest x value for y equals tangent of x becomes the lowest y value for the arctan. The highest x value for the tangent function becomes the highest y value for the arctangent function. All right, so it's just a matter of drawing it with the appropriate shape. All right, so as you go out to infinity, where are you going? You're going to whatever that horizontal asymptote is. All right, that's going to be pi over 2. All right. So pi over 2 minus the arctan of 1. Arctan of 1, well, somewhere along this graph, pi over 2 is about 1.57-ish. 1, you say that's 1 right there. That's going to correspond to a particular angle. You want to know what that angle is. Well, you want to be thinking about what angle has a tangent in the unit circle, a tangent value of 1 within the appropriate domain. For tangent, you're really looking at, well, the y values are going from negative pi to pi. So in the unit circle, you're thinking fourth quadrant and first quadrant. So for a positive 1, that's got to be the first quadrant for tangent, because tangent's negative in the fourth quadrant. That happens at a 45-degree angle, which is pi over 4. So pi over 2 minus pi over 4 is going to be pi over 4. Alright, so it's like, oh, all stuff that you should know. I mean, this problem kind of sums up everything up to and including Calc 2, to this moment in Calc 2. It's a pretty good exemplar problem. If you can handle this, you're pretty good shape. All right, but we also didn't answer the question. So what are we talking about? Well, the limit converges. All right, so the limit converges onto this particular value. So converges. So therefore, we would have to say that, and the more you kind of take up space like I do, the more you got to find room to squeeze stuff in, which again, an app is really useful when it comes to that. So therefore, the sum from n equals 1 to infinity of 1 over n squared plus 1 converges by the integral test. All right, so all these conditions came into play to set up the integral test, that whole decreasing, positive, continuous. But then once we determined whether the limit existed, the limit of the all that good stuff, then things started working out. All right, or at least leading us to a conclusion. All right, integral test remainder approximation. If the series converges to S, all right, so S is in some sum, then the remainder, also known as the error, R sub n is equal to S minus S sub n, is bounded by that, a little formatting error, right? But it's between, that remainder is going to be between 0 and that integral, all right? So S is equal to that S sub n. That S sub n is talking about the partial sum, n terms out. That partial sum plus the integral going the rest of the way can give you the actual sum, or at least it'll give you some upper bound related to the actual sum. The sum has to be lower than whatever you get using that computation. It's a good way to come up with an approximation. All right. So what we would do here, for example, in this one, it says using 6 terms. So let's go out 6 terms here. So 1 over 1 to the 4th, 1 over 2 to the 4th, 1 over 3 to the 4th, 1 over 4 to the 4th, 1 over 5 to the 4th, 1, 2, 3, 4, 5. Well, I don't even know why I did that, because the number of the term is written right in the value itself. Now, I don't personally want to figure this out by hand, because we could go on and on and on, but they only want us to go 6 terms. So if I want S sub 6, I'm only adding up the 6th partial sum. We have our calculator set up to do that. All right, so that's in, again, the parametric menu. So mode parametric, go into y equals, start deleting stuff, because this one's way less complicated than the one that we had, or I had in there originally. So t to the 4th instead of n to the 4th, as we know by now, hopefully. All right, so I only want, like I said, to go out to 6 terms, so I'm going to go into my table, which is, if I remember correctly, set up for another problem. So let's go table set, second window, 0 to 1 as my default. My 6th partial sum is this lovely decimal. All right. So, I mean, if we wanted to, I suppose we can come up with a fractional value, but this is going to be fine because we are looking for an approximation, so this is what we're going to live with. 1.08, I'm going to write the whole thing, 11233534. All right, so what we're going to do now is find the integral going the rest of the way. All right. So the integral of what? Well, we're going to kind of steal a little bit of our thought process from the integral test, and that is continuous function decreasing positive. All right. So if I go back into function mode, verify that 1 over x to the fourth is a positive, let's make that a 4, decreasing continuous function on the appropriate domain starting with a 1. It looks like we're good there. All right, so I'm going to let f of x equal 1 over x to the fourth. What I'm going to do is find the integral going from 6 to infinity. No longer am I going from 1 to infinity. 1 to infinity would give me, really, it's an approximation because all you're getting area under a curve, but for lots and lots of unnecessary points. All right. If you go from 1 to infinity, you're not capturing area under a discrete value. Discrete value, just individual points. That wouldn't make sense. All right. You're getting all the space in between the number 1 and 2, and the number 2 and 3, and the number 3 and 4. But the thing is, the difference between the area under the curve for large values of n and the actual fractional values added together, those sums, is so negligible that we can get away with it. So that's where this idea comes into play. So I'm going to find the integral over this interval, which gets swapped out, or at least adjusted, limit as a approaches infinity, because it's still improper, going from 6 to a of, and I'm going to write this because this is kind of nice. I'm going to write that as x to the negative fourth dx. Can't always count on something being that nice, but it's very nice in this instance. All right, so I'm going to increase my exponent by 1, divide by the new exponent, going from 6 to a, so it's still limit as a approaches infinity. So the limit as a approaches infinity of negative 1 third a to the negative third minus a negative, so plus 1 third 6 to the negative third. All right, I'm going to clean it up. And then the cleaning part is not going to be too substantial, but it's still something. I'm just going to resize a little bit first. Just a little bit. So then I'm going to rewrite this as the limit as a approaches infinity of negative 1 over 3a to the third plus 1 over, well, 6 to the third is 216, so 3 times 216. All right, 6 to the third, 216, but it's negative, so it goes on the bottom. So the limit as a approaches infinity of this, what is that, 648? So this component here is going to go to 0, plug in infinity for a, negative 1 over infinity is going to go to 0. The other part is constant, so this whole limit is going to boil down to 1 over 648. All right. So we ask ourselves, well, what did we just get from that? All right. So this piece, the part that I was apologizing for in terms of the formatting, we have a remainder that's based off of that integral that we just computed the value of. All right. So we know that the series is going to converge to S. All right. So I can make a little note of that. So this whole thing is going to be S. All right. That S is going to be thought of as the sum. So think of S as the sum of the first term, or the first n terms, the first n partial sums of the series expansion plus some leftover stuff. All right. So what we did was we figured out that S sub 6 was 1.08 blah blah blah. All right. So this rule is telling me that S has to be equal to S sub 6 plus R sub 6. That's not a 6. R sub 6. All right. What we get by computing the integral is the remainder, R sub 6. That's what this is. So 1.0811 blah 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 plus at most something less than 1 over 648 will give us the sum. All right. So that's the weird part. It's not the case that the sum is equal to, the sum of the entire series is equal to these two values added together. It's the 1.0811 blah blah blah, which we know to be true. That's finite. We figured that out. Plus some other number that must be less than 1 over 648. Why? Because we have this graph what we did was we figured out the sum of the first 6 values. So let me bring it in. 1, 2, 3, 4, 5, 6. We actually figured out these values. We added them all up. Then at the end, we got lazy and we said, you know what? I'm not going to add them all up anymore because it's going to take the rest of our lives. Let's just get the area underneath the curve. So this is an overestimate. All right, so whatever that value is, it's got to be more than, maybe way more than, maybe only a little bit more than, but more than what the true value would be if you were to just add up the points along the way. But since we don't have the time, patience, and resources to spend lifetimes going out to infinity to figure this out, we live with that overestimate. All right, so that's what the R is going to give us. It's going to give us an overestimate. So 1.0811 blah blah blah, we know that that's the first 6 terms of the sum added together. The remaining part of the sum, so if I were to go out to infinity, everything else from the 7th term on to the infinity term would never amount to more than 1 over 648. All right, so 1 divided by 648, 0.00154. So the first 6 terms will add up to that 1.0811. Everything else is going to add up to nothing more than 0.00154. If you're comfortable with that, then what we do is we use an estimate, that S sub 6 as an estimate of the true sum, and make a note that we're accurate to less than, what would that be, 1/100th, all right, of a unit, all right? So we would be looking at that would be 0.154%. Yeah, so less than 1% of a unit. All right, so we would be pretty comfortable with that in some cases. All right, so this is the approximation, and this is the max error.